Hello, my name is Michael Suplee, and I'm in the Water Quality Standards and Modeling section at the Montana Department of Environmental Quality. Today I'd like to talk to you about the triennial review of the base numeric nutrient standards and nutrient standards variances that we recently completed here at the department. Before I get into the details of this review, I thought I'd give you a little background on triennial reviews in general. The Federal Clean Water Act and also state law requires that we review our water quality standards every 3 years. The main document that is typically reviewed or has been reviewed by the department most commonly is DEQ 7. This is the one that contains our carcinogenic, toxic, and harmful parameters, and there are rules associated with it. However, in 2014, the department and the Board of Environmental Review also adopted two new circulars, DEQ 12A, which pertains to water quality standards for nutrients, nitrogen and phosphorus, and DEQ 12B, which pertains to nutrient standards variances, or variances from nutrient standards for specific situations where dischargers cannot achieve the nutrient standards immediately. There are also associated rules. The presentation that we're going to be looking at today pertains specifically to this set of circulars and rules. Now within this group, there are actually two circulars, as I pointed out, A, which pertains to the standards, and B. Although we considered both of them initially for the review, this triennial review, there were no new numeric nutrient standards developed at this particular point in time, and so there was nothing to address in Circular DEQ 12A. Therefore, the entire presentation that you're about to see will focus on Department Circular DEQ 12B, which pertains, again, only to the process by which a variance is granted from the nutrient standards. So as I pointed out, under the Clean Water Act, we review our circulars every 3 years. That's also true under the Montana Water Quality Act. And specifically for nutrients, we have statute that requires us to review the specific groups that are in DEQ 12B that may receive a variance. There are three general categories of variance recipients described in statute. That would be the group of discharges whose discharge is greater than or equal to 1 million gallons per day, the group that discharges less than 1 million gallons per day, and people or communities that have lagoons for treatment systems. Currently, this group, the greater than 1 MGD group, has a requirement that if they can't meet the numeric nutrient standards, those found in Circular DEQ 12A, then they need to treat their wastewater to at least 10 milligrams total nitrogen per liter and 1 milligram total phosphorus per liter. If they're in the less than 1 MGD group, those numbers become 15 milligrams TN and 2 milligrams TP. And if they're in a lagoon, or using a lagoon, then they are expected and required to maintain their current performance. So beyond that, Circular DEQ 12B directs us how to carry out the triennial review for each of these three groups. They'll be looked at on a statewide scale, and we will consider the aggregate economic impact to dischargers within each category. And much of what we'll be seeing in this presentation pertains to the detailed analysis of each of these three groups. As I mentioned, in 2014, circulars A and B were adopted. However, in 2015, about a year later, the United States Environmental Protection Agency updated its rules regarding variances. These changes made at the federal level had a significant impact or effect on DEQ's triennial review, which we would have carried out anyway. The three most important components of the federal changes that affect our triennial review is their requirement now to identify a highest attainable condition, or HAC, which I'll be discussing later, the amount of time it takes to achieve the HAC, and something called a pollutant minimization program. We'll be looking at all three of these as we go through this presentation. So what is this highest attainable condition? In those cases where the nutrient standards can't be attained because of the limits of technology or cost, it's essentially an evaluation that is identified mainly based on economic impact considerations. This graph presents to you in a generalized way how the variances were originally set up in 2014 when they were first adopted, and contrast them to what they would look like going forward with the proposed rules. The black line shown here represents the conceived process as it was laid out in 2014 in guidance and in rule over the 20-year variance period that was allowed in statute. The idea here, for example, for this greater than 1 MGD group for total nitrogen, is that some particular facility may be beginning here with concentration somewhere around 17 or 18 milligrams total nitrogen per liter. They would do a series of treatment improvements to get down to around 10 milligrams per liter over about a 5-year period. The next step would be that they would reduce those again down to 8. And from this point forward, it was not exactly clear technologically or economically how this would occur, and so this was kind of an unknown area in the future. However, the way it was laid out, ultimately, they would be expected to achieve the numeric nutrient standards at the end of the 20-year variance period, and that meant that the numeric nutrient standards represented the highest attainable condition. Going forward with these new rule changes, it's a similar starting point, but as you can see, facilities will be looking at making changes over time to improve their wastewater quality, and eventually they will ultimately have to treat to something, but that will be defined as the highest attainable condition here. This is the main distinction between how the rules were established originally in 2014 and how they would be operating going forward from this point. So where will this highest attainable condition be found? In Circular DEQ 12B, there is a table, 12B1, which currently contains the treatment levels that we looked at earlier. This is the 10 milligrams total nitrogen per liter, expressed here as micrograms per liter, thus the extra zeros, and the 1 milligram total phosphorus. Same here. This is 2 milligrams TP and 15 milligrams TN. These are the numbers that we will be looking at and updating and have been examining as part of this triennial review. So wastewater treatment cost estimates to identify HAC. How are these done? Well, we looked at each of the 3 categories individually, the greater than 1 MGD, less than 1 MGD, which, as I probably mentioned, are mechanical facilities. We looked at lagoons, and we coordinated these analyses and discussed them and the results with the department's advisory group on this topic, the Nutrient Work Group. We held 4 meetings between September of 2016 and March of 2017, and in and amongst those we had 5 technical subcommittee meetings in February and March as well to go into greater detail of some of these analyses. The basic process by which we identified highest attainable condition was, for the greater than 1 MGD group, we first identified a range based primarily on cost to the group. How much would it cost the group of dischargers that need a variance to achieve different treatment levels? We then discussed those results with the Nutrient Work Group, received their input, and we also compared the output and the results to other biological nutrient removal facilities that have dual nutrient control and that are being operated around the country. For the less than 1 MGD group, we did the same thing, identified that range based on cost. We then also looked at a little bit further detail of the cost for future collection systems, and we also relied on engineers' judgments as to what advanced operational strategies or plant optimization, which is another way to put that, can achieve. For lagoons, we examined the cost for a random sample of lagoon-based communities using a similar process but on a more limited basis than we did for the other 2 groups. So this is a summary of the ranges that were found based on cost analyses and some of the other materials that I just mentioned. and we'll look at the details of each of these going forward. For the greater than 1 MGD group, it was found that the highest attainable condition falls somewhere in the 4 to 7 milligrams total nitrogen per liter range, and the less than 0.1 to 0.4 milligrams total phosphorus per liter range. For the less than 1 MGD group, it would be something significantly higher than 7 and up to possibly 10 milligrams total nitrogen per liter, and right around 1 milligram total phosphorus per liter. And for the Lagoon discharge group, the analysis revealed that there should be no change to the current method of implementing the general variances. So let's start with the Lagoon group. We randomly selected 8 communities that use lagoons for treating their wastewater. And what is shown here in this graph is 5 different treatment levels that were estimated for these communities and how much it would cost each of them to achieve these different levels. So for example, this first level here would be the treatment cost for 3 milligrams and 0.05 applied as land application. The rest of these, which range from 7 all the way down to 3 milligrams total nitrogen per liter, obviously these being more stringent requirements, are all variations on the replacement of the whole lagoon with a mechanical facility. We then looked at the number of individual members of this sample who could afford to meet this treatment level. As you can see, 38% of the 8 communities could afford land application, but still it was a minority of our sample. When it came to complete replacement of the lagoon to a mechanical facility, none of the treatment costs, even the most coarse level treatment one, was affordable for any of the 8 sampled communities. So this revealed to us that as a group, there was no treatment technology change that would allow them to go to something more than what they're currently doing based on these cost analyses. Now, for the greater than 1 MGD and less than 1 MGD mechanical groups, we first wanted to focus only on those facilities that were actually likely to need a variance. So we carried out a series of analyses to determine who would actually require one. That's what these pie charts show. So for example, in this group, the greater than 1 MGD group, there are actually 6 facilities out of the 21 that already are meeting their waste load allocation, or they have no reasonable potential to exceed a water quality standard for nutrients. In other words, anybody in this group does not need a variance because they basically can meet the nutrient standards today. Some facilities are discharging in locations where there are no numeric nutrient standards for nutrients adopted. That would be these cases. For the remaining 10, these are facilities that we identified as would be likely to need a variance. Same analysis was carried out for the less than 1 MGD group. In this case, 14 facilities, or about 38% of that group, are likely to need a variance. The cost analyses to go to various treatment levels that we'll be looking at in just a moment is only focused on the groups in this red slice of the pie from each of these 2 discharge groups. This chart represents the cost analysis, and it's very similar to the one we looked at for lagoons. Again, on the y-axis, we have the percentage of group members evaluated who can afford the treatment level. And on the x-axis, we have 6 different treatment levels that were analyzed, and the cost estimates to meet these different treatment levels were calculated by engineers. Again, ranging on the left, the most coarse level of treatment of 7 milligrams total nitrogen per liter and 0.5 milligrams total phosphorus per liter, all the way down to 3 milligrams TN and 0.05 milligrams TP, which are considered the limits of technology. The error bars are based on a high and low estimate that was provided by the range that the engineers said was the error bar around the cost estimate that they provided. What this shows is that for the less than 1 MGD group, essentially only a minority of the group can afford even the coarsest level of treatment. In other words, there is no treatment level that we examined that they can afford to meet as a group in the majority. In contrast, for the greater than 1 MGD group, there are cost levels for limits of technology and some of these here that I'm pointing to that are essentially unaffordable. But then we move into cost levels that are within the affordability range for these facilities, especially the 7 and 0.5 milligrams category, where a minimum of about 65% and perhaps as many as 85% of group members can afford to meet that treatment level. So looking at a little bit more detail for the greater than 1 MGD group, we examined the actual discharge quality of a whole series of dual nutrient control facilities that have stringent nitrogen and phosphorus limits in their permit limits. And what you can see, all of these facilities are greater than 1 MGD, just like the group we've been dealing with. Some of them are here in Montana, many of them are in other parts of the country, but these folks are achieving water quality levels within that range of 4 to 7 milligrams per liter TN and 0.1 to 0.4 consistently, because this data that I'm showing you here is their 95th percentile performance. In other words, they're achieving these levels 95% of the time. And so that indicated to us that real-world facilities working in real communities do actually and can achieve these sorts of water quality concentrations in their effluent. Now, as I mentioned, we looked at in further detail at the cost for collection systems, especially focusing on the less than 1 MGD group. We actually built into our cost estimates, the ones I was showing a moment before, what we figured would be a small and likely underestimated value for collection system cost upgrades. But further analysis by one of our engineers in the group suggested that the smaller communities, those that typically fall into the 1 MGD group here, are likely to carry much heavier burdens in terms of future collection system cost replacements, because there are fewer people in the community to spread the cost across when pipes in the street need to be replaced or need to be relined or lift stations need to be upgraded, etc. And those can actually be a pretty substantial part of their community median household income. So what these data indicated to us was that for that group, the less than 1 MGD group, we should select the highest attainable condition that leans towards the upper end of the range, because these folks are likely to be looking at significant additional costs that we have not rolled into our estimates when it comes time to upgrade their collection of systems. Based on the materials that we just looked at, these are the current and then proposed changes to the treatment requirements, those in white basically reflecting the highest attainable condition. As you can see, for the greater than 1 MGD category, the levels of nitrogen and phosphorus have both come down a significant proportion from what they were currently. Also the case for the less than 1 MGD category. And for lagoons, because the costs were essentially unachievable for almost all the technologies we looked at, there will be no changes in the way we're permitting lagoon variances, other than to implement a pollutant minimization program, which I'll talk about shortly. Now, what about the time it takes to achieve the highest attainable condition? Is this expected to occur immediately or within a permit cycle? No, that's not necessarily the case. We've identified, along with our engineers, about 9 steps that it would take to go from current conditions to achieving the HAC. And what these are is they're a combination of advanced operational strategies or optimizations combined with actual facility upgrades. And if it takes fewer steps than these 9 for a particular facility to get to the HAC, then less time would be required to do so. This graphic illustrates the idea. So, for example, for Facility A is starting out with concentrations in their facility somewhere around 15 milligrams per liter, and the highest attainable condition has been identified as 6 milligrams TN per liter. Initially, they could work on optimizing their existing facility It might have significant success with that, as we have had a number of examples of that around the state over the last 5 years. But there might be a point, and there's likely to be a point in the future, where optimization simply won't take the plant any further in terms of the quality of the effluent it can discharge. That's this point here. At that point, the facility can begin looking at designing and funding to ultimately institute a upgrade to the facility here. Capital improvements project would be implemented, and usually we would see a significant reduction in nutrient effluents. And finally, then they would go through some additional optimization steps. But if these were not able to achieve the highest attainable condition, then they could go through a smaller design and funding phase with a smaller capital improvements project, ultimately to achieve the goal of the highest attainable condition somewhere out towards the 20-year timeline that is allowed under the variance. This would probably be about the longest timeline that a particular facility might need to do this. In contrast, Facility B, for whatever reason, has started out with effluent of higher quality, and with optimization has gotten pretty close to the highest attainable condition, and then only had to go through a single capital improvements project to ultimately achieve it in fewer years. We expect that these facilities around the state that need a variance will vary considerably in terms of the amount of time that they'll actually need to go from where they are to the highest attainable condition as time goes forward. So this table here represents what the treatment requirements are going to look like going forward, at least as they're proposed. These are represented in milligrams per liter. As you can see, there's the 0.3 and the 6, the 1 and the 10, and maintain long-term performance for the lagoons. Now, since 2014, when the rules were initially adopted, if a facility was treating wastewater better than the water quality values in the table, this table and its predecessor, their actual treatment levels define the permit limit. And that will be the case up through July of this year. This is because most of those communities or companies were able to achieve those concentrations and presumably without incurring substantial and widespread economic harm. However, going forward, if a facility does not meet the levels in the table on July 1st, but then meets them later, the table values themselves define the permit limit. And that's because the values in the table value now represent the highest attainable condition determined via economic means. So for example, if a community was in the less than 1 MGD category and they're currently discharging at 14 milligrams TN per liter, and they were to do some optimization or upgrades or some combination and get down to, for example, 8 milligrams TN per liter, their permit limit would not be based on 8 milligrams TN per liter. It would be based on 10, as shown on the table. Optimization was a requirement in order to receive a general variance since the initiation of our rules back in 2014. So those always had to be completed. Going forward, they'll be required to be incorporated into the facility's operation and maintenance manual. And earlier I mentioned that we have a new requirement under the federal law called a pollution minimization program. Those are to be required to be put in place when a facility actually achieves the treatment requirements in Table 12B1 or the HAC. The point being is that if it takes some years for a facility to achieve the highest attainable condition, they don't need to do the PMP right away. They do the PMP at the time that they actually achieve the highest attainable condition. And as I mentioned, the time to achieve the treatment requirements will vary from facility to facility. One nutrient may be achieved first, in which case the PMP will be required for it first. So what is a PMP exactly? It's defined as a structured set of activities to improve processes and pollutant controls that will prevent and reduce pollutant loading. Some examples of this would be that a facility may want to reduce or try to reduce pollutants before they ever enter the wastewater treatment system. This is commonly done in larger cities. Or, for example, it could be the case that a A point source could work with an upstream non-point source, a rancher or farmer, to mitigate some pollution point sources in that regard, and so that the water quality in the receiving stream is better. Those BMPs that were implemented would be also considered a PMP. Another change that we are recommending for this triennial review is a change in one of the aspects of the permitting process called the coefficient of variation. This number, which is used to calculate the permit, is essentially a measurement of how variable the effluent quality is. If effluent quality is very consistent and is almost always the same, it'll have a very low CV. If it's highly variable and changes a lot from day to day, then it will tend to have a high CV. And right now, the way permits are developed is the CV is based on past results or past data. But what is known is that the CVs are likely to go up when lower nutrient effluent concentrations are achieved, because that's just the basic nature of how it works with nutrients, because they're harder to continually maintain at lower concentrations. And this could lead to compliance problems. So we're proposing a fixed CV of 0.6, which is commonly used in permitting, especially for small data sets, which is the case here, as being more appropriate for when nutrient effluent concentrations are low. This CV value should be reviewed in the future. In 2014, along with the rules and the circular DEQ 12A and B, DEQ also published a guidance document which was intended to help the department work into the further details of very technical aspects of the implementing the rules. But it's not actually part of the rules. But we will be updating this document nonetheless. Some important changes or lack of changes that I'd like to point out is that we are not going to be changing the definition for the limits of technology that are currently in this guidance document. They will remain as 4 milligrams TN per liter and 0.07 milligrams TP per liter. We will be deleting section 2, the nutrient reduction steps, and replacing them with a description of the process for identifying highest attainable condition, along with some of our lessons learned as we've developed the highest attainable conditions. And finally, we have supplemented section 3 with additional guidance on individual variances, as we anticipate that more facilities may be looking to pursue individual variances going forward, and so we've provided some additional guidance on those in this section. Finally, I'd like to present to you the general timeline for the rulemaking. On April 14th, last week, the Montana Administrative Record notice was published that the rulemaking had begun, and so that essentially started the rulemaking process for this triennial review. Out on our website, we're at the same location where you found this video. You can find the track changes version of Circular DEQ 12B. You can also find a technical report on the triennial review. On May 31st, here in Helena, at the DEQ in room 111, we're going to have a public meeting from 9 to 12 on the rules and changes. Then on June 23rd is the publication date for the adopted rules that we will have updated. And all that should be completed before Circular DEQ 12B expires on July 1st, 2017. I want to thank you for listening to this presentation. I provided my contact information as well as that of Mila Kelly, our supervisor. If you have any questions of any kind or would like to discuss any of this, please feel free to give us a call or to send us an email. Thank you very much.